calculate standard error. Okay, now we're going to repeat this study. We're going to leave Manhattan, we're going to go to Brooklyn, and we're going to repeat this study for 16 pubs and find that a mean of 34 beers and a standard deviation of 7.1. Okay, let's go back here and take a look at what our knowledge of this is now and how it compares to what we knew before. Okay, I'm going to get a new page. Whoops. Okay, here's our new page. And we got X bar, we've got a sample size, and we've got a standard deviation. Okay, and what was it? Sample size is equal to 16. Our standard deviation, our mean was equal to, I believe, 34. And let me see our standard deviation as well in here. 7.1. So our mean is 34. And our standard deviation is equal to 7.1. Okay, now we got a small sample size, right? Instead of a big sample size, we have a small sample size now. So now we can't assume that our distribution, that we know our standard deviation well enough, or sigma well enough for the population well enough to avoid some extra uncertainty from having to guess at the standard deviation. So how do we make up for that uncertainty? We use a t-distribution that's determined by the size of the sample. The t-distribution is going to be spread out more for a smaller sample because we have more uncertainty, and it's going to be spread out less for a bigger sample because we have a bit less uncertainty. Okay, if we have a really big sample, the t-distribution is basically the same as the z-distribution. That's why we say with a sample size of 300, 200, or 300, we're not going to bother distinguishing between the two because when it's so big, that t-distribution is almost identical. Okay, so let's see how we're going to work this out. So we're looking for a 95% confidence interval now. How are we going to calculate that? Once again, it's going to be X bar plus or minus. Well, this time we're not going to use the Z distribution. We're going to use the T distribution. And that T distribution is going to be specific to the level of uncertainty we want to accept. In other words, our confidence interval. T times our standard error. Well, let's calculate our standard error. Standard error is calculated the same way, except this time it's standard deviation over the square root of the sample size is equal to 7.1 over the square root of 16, which is 4. And I'll calculate that now. I'm sorry, 1.775? Okay, great, thank you. 1.775. Okay, good. That's our standard error. So now our calculation for our confidence interval is going to be 34 plus or minus our t-value. What's our t-value going to be? Well, we can do that a couple of ways. One way is to look it up on the table. Okay, I want to get the table up too so everybody can see where it's coming from. Okay, so if I can't expand that. Okay, so how are we going to look up our t-value? Well, our degrees of freedom represent basically our sample size, right? Degrees of freedom are sample size minus 1. So for our purposes, the line we're interested in here is the line 50. First of all, number one, why is it organized this way? Why don't we have a table like we do for the Z table, where we have areas in the middle and the t-score on the outside? Why do we have it this way instead? Right? Because really, we could do it that way. The problem there is that for every sample size, we would have to have a different table, right? So we would have to have one table for 2 degrees of freedom, one for 3 degrees of freedom. We'd have to fill out a manual, a book full of tables, right? So most of the time, we're only interested in 95%, 99%, 90%. So why bother with all those other areas? Why know, as long as you know what T is for a certain sample size, for a certain T distribution, for 90% certainty, 95% certainty, 99% certainty, that's plenty for us, right? So in fact, we actually have more. We have the 80%, we have 90%, 95, 98, 99. So, but most of the time we're going to be interested in 90, 95, or 99, and almost 90, and most of the time, just 95. So for 14 degrees of freedom, was it 14? No, we started with 15 degrees of freedom. We started with sample size of 16. What's the t-value that we want for our 95% confidence interval? It's going to be 15 is this row over here. So which row is that? That's this one right here. Now notice that it says the confidence level is 95%, but it describes the right tail probability as 2.5%. T-score for 2.5%. Take a look at that in a second. So I'm going to just get that number for now. So let's see, 15 degrees of freedom is going to be 2.13. I'm just going to round it off to that. So our T-score is going to be 2.13. Write that in there. 2.13 times our standard error, which is 1.775. Okay, now let me go back to this for a second. So let's see what does that exactly mean, that T-score is 2.13? Well, the normal distribution, the Z distribution, looks something like this. And 95% of that distribution is between 1.96 standard deviations to the left of the mean and 1.96 standard deviations to the right of the mean. My T distribution has a similar shape, but it's wider. And the lower the sample size is, the wider is that distribution. So for the T distribution, 95% of the outcomes is going to be further out than for the Z distribution, right? That's where the 2.13 comes in, because it's the number of standard deviations away from the middle, or the mean, the point value, that you have to be, so that 95% of the population, 95% of the outcomes or population, whatever, are between those two Z-scores. Okay, well, what does that mean? That means that there's 5% left, so 2%, 0.025, on each end. So that's what it's describing there on that table. It's describing 0.025. If I can get back to it again. You can see. I can never remember what my shortcut is for this. Let's see. I put the table away. There's the table, okay. So if I go back here and look at this, it says, 95% confidence interval. That's the same thing as a right tail probability of 0.025. Well, it's interesting they put that there, because really we're interested in the two-tailed test most of the time. But if you look at that, a right tail probability of 0.025 implies that you have the symmetrical probability on the other end, the left side. So you have 2.5% and 2.5%. That's why they put that there for the right tail probability. And it is the same thing as saying a 95% confidence interval. Okay, so that's what that table is. That's what that table's doing to us. Okay, so let's take a look at how this works out. So our 95% confidence interval here is going to be equal to, I'm going to pull up my calculator so we do it. Okay, let's see. First I'm going to work out my margin of error, 2.13 times 1.775 equals this, and I'm going to clear out my memory first. Put that value into my memory, clear. Okay, so 34 minus our margin of error. Did I hit the minus? Minus our margin of error. Let me clear that. 34 minus our margin of error. I killed it, didn't I? Try this again. 2.13 times 1.775. Okay, I'm going to put that into my memory. And I just hit memory clear. Put that into my memory and clear the register. Okay, 34 minus, call my memory. That's going to be 30.2. And round it off for our purposes. 30.2. And the upper value is going to be 34 plus our margin of error, 37.78, or 37.8, I'll call it. Okay, there we go. So 30 to 37.8. That's quite a bit wider than our margin of error was before, right? This is only your margin of error there. Our range before was only 4. Now our range is almost 8, right? So that's quite a bit wider, and that's attributable to to using the t-value, because our standard deviation was only a little bit different, right? It wasn't twice as much. It was only about maybe 15% different, right? So not being able to use the z-distribution, working with a small sample, reduced our certainty about where the middle of this is, right? So that's one of the reasons why a big sample is good, because it increases your level of certainty, okay, and reduces the